Over the next week, we're going to learn to write our first WebGL programs, and there's a bunch of interlocking pieces that we have to discuss. In this lecture, what I want to talk about is mostly about the development of OpenGL and why it came to have the form it does, and that'll get us into, in the next lecture or two, get us into discussing different ways of viewing the OpenGL web architecture under which WebGL is one of the forms. And then we'll get into what do the functions look like, the details of the syntax of the functions, and building up to how do we write a simple program. Although that it'll be simple, just display a square, it'll have all the elements of the more complex programs that we'll be developing throughout the course. So this is the path we'll follow for about the next week. And that'll also, the end of that, we'll start getting into how do we write our own shaders, because as I've said, the shaders are going to be where the action is. So let me start at the beginning and go way back to, it's 40 years now, to 1973. There was, if you hark back to the earlier lectures where I talked a little bit about development of hardware and software, around the 70s we were starting to get our first graphic systems, or first raster graphic systems, and there were some commercial systems coming out. There were also graphic terminals that were around that could be plugged into a standard computer. We also were starting to get our first PCs and workstations. So people were seeing that graphics was going to be a standard part of any computer system. And so various committees were trying to standardize the software just as they had with various other languages, whether it was Fortran or anything else that was around at that time. So the organization that had been doing that was the International Federation of Information Processing Societies, and they in 1973 formed two committees, one that was primarily in Europe, and they came up with the graphical kernel system, which was a 2D, only 2D system, and a group that was primarily North American that came up with a 3D standard that also had a 2D part of it, which was called the core standard. There were major differences between this that partly were due to the difference between one being 3D and one being 2D, but also because of the nature of the groups. The European standard was a much more academic standard that had been formed by the people who had experience with the first real standard, the Algol standard. And so they were very academic and very careful, even though they knew that the standard they were coming up with was very limited. In the US, where workstations were under development and becoming available, at least to the defense industry, the airplane design industry, who could afford these workstations, which were fairly expensive then, they were interested in three-dimensional problems. So it didn't have the sort of the academic purity and the care that the GKS standard had, but on the other hand, it was something that was more useful to the application programmers out there. But what happened was that GKS was adopted by the International Standards Organization, ISO, as a standard, and later became a U.S. standard, the ANSI standard, somewhere in the 80s. But the problem was that because core didn't become a standard, and it was the 3D one, the people who were doing the design work and the CAD work were kind of left out in a way, because when you try to take a 2D standard and make it 3D, you get into all kinds of problems. And so when they try to extend GKS to GKS 3D, it just didn't work very well. And it was, at that point, it was way beyond what was really going on in the workstation community, in particular with hardware. Core was included in the first Sun workstations. We had the first Sun 2 workstations in New Mexico, and it was on those stations that I started teaching computer graphics with them. Core was interesting. It had problems, but it was truly from having nothing, just being be able to put pixels up on the screen and draw lines to have something that had a real 3D software, and it was a real advance for us. But on the other side of things, the more commercial side, the people who were working in the CAD community said this is just really not meeting our needs, either of these standards, and they started working on something that was called that's called FIGS, that still has some interest. A lot of things were derived from it, and that stood for the Programmer's Hierarchical Graphics Interactive. I left interactive there. Hierarchical Interactive Graphics System, and in a way that includes everything you want your system to be, to be able to support hierarchical complex models, to be interactive so you can do design, and of course to have the graphics part of it. So that was an industry standard. It was very much based on a shared database model, so that because it came from people in the aircraft industry, and where they were in the more bigger CAD industry, where you had a lot of people working on a project, so you wanted to be able to share data. So there was a lot of attention paid to being able to support some moderately complex data structures that could be shared among multiple users in different places. So it wasn't particularly good at interactivity in the sense we see it now, but on the other hand, at that time it was pretty good and supported raster workstations. In parallel with that was going on an effort to develop the X window system, primarily through DEC and MIT, and what that did was bring about the importance of a client-server architecture, and probably behind a lot of this was the work that went on at Xerox PARC, which really went a long way to saying a standard workstation would always have graphics and some sort of an interactive device like a mouse in addition to a keyboard. So that sort of preceded this idea of trying to get a standardized X window system, which is the one we still use now in our Unix systems and others. There was an effort to combine the graphics and the CAD part with the X window system, and there was a standard called PEX, which was FIGS extensions to X, and it had everything that was in FIGS added on to everything that was in X, and it wasn't very easy to use just because it was so big, and since neither system was perfect, it had all the defects of both included in this massive system. So I suppose there's still some people out there using it, but it was just too big and complicated to really be useful. Now, about at that time, Silicon Graphics came out with their workstation, which had the pipeline implemented with VLSI chips, and that completely revolutionized the field because you could produce these very powerful workstations at a very reasonable cost at that time. So it opened up computer graphics to other communities like advertising, and animation. Some of the film people started working on early movies with them. Now, to use that system, Silicon Graphics created something called Iris GL, GL obviously meaning graphics library, and the idea was to have something that so application users could program this system. But some of the really good things about it was that, one, it was very, very straightforward. I found out about this from my students who had gone to work at Sandia and said, hey, this is way better than anything we've used. Why don't you try it? And we traded for our first Silicon Graphics workstation and got it. And it was very simple to program, and it had this characteristic that it was nice to program on from the high end, from the application programmer's end, but it was very close enough to the hardware that you could develop very, very very fast interactive code. And so it was clearly better than anything that had been around, but it was tied to the Silicon Graphics workstations, and so it had windowing in it and it had input in it that was very hardware specific to their systems. But it was so successful that Silicon Graphics came out in 1992 with the first version of OpenGL, which was a platform independent API that was close to Iris GL, but what they had to do was take out the windowing and the input because that was so system dependent. So the idea was that here's a bunch of an API with a bunch of routines in it that will let you render. It'll let you specify objects and how you want them to appear on the display, their colors and their orientation, and it was a full 3D system. But you now will connect that with your own windowing system and your own input system, so it could, in principle, work on Windows and work in Unix systems. And in fact, that was true. Now, originally, that standard had an architectural review board, which was pretty much dominated by SGI at the time because they were the major player in computer graphics, but it also had participation from Microsoft and HP, and later when companies like NVIDIA formed that were producing GPU chips, they became part of it. Now it's been replaced by the Kronos group that sets a number of standards, not only the OpenGL standard, but the OpenCL standard, which allows you to do computing on numerical computing on GPUs, and a number of other standards. Now, in terms of the standard itself, it was pretty stable and going through, and it didn't change very often. And this was really in opposition to what was going on in Microsoft, where the various versions of DirectX would come along fairly rapidly. They would not be backward, or they wouldn't guarantee you any backward compatibility. So but they were appealing for the most part to a different audience, an audience that was pure Windows, and probably more important, they were an audience that was really just concerned with gaming, and so the gamers were always wanted to get at the latest hardware, and so DirectX would respond to support that, while during this period, let's say in the 90s and the early 2000s, where OpenGL really appealed more to the scientific and engineering community, which really valued stability in the standard. So all through version 2.5, things would change a little bit, but you were always guaranteed to have backward compatibility, so that you would know that if you had developed a program and you got a new version, upgraded version of OpenGL, your old program would work. It evolved to have new hardware capabilities during that time, so it could support, went from being able to support 2D texture mapping to 3D texture mapping, and you started to get the ability to write vertex shaders and fragment shaders. But it was at that time based on a fixed function pipeline where you didn't have much control over the shaders, and slowly we got the ability to change the behavior of those shaders as the hardware improved. Now, when we got a little bit past there to what we say is a more modern OpenGL, this is the picture we've talked about before, where we say, well, now all of this goes on the graphics card and is in the GPU, and really what we want to do is use the power of the vertex processor and the fragment processor and process this stuff not in the CPU on the main system, but rather through shader which are programs that go into the vertex and the fragment processor. And this has been an immediate change. Going along with that change is that we've gone from what was called immediate mode graphics, and we'll see a few examples of this when I look at some demo code probably in the next lecture, where originally all these systems were immediate mode graphics, which said that what you do is you specify your objects. Your objects are described, as we've seen, by vertices, because vertices can be used to build up the higher level 2- and 3-dimensional entities we want to work with, points, lines, and go past that to curves, circles, surfaces. But they're all specified through vertices. And in immediate mode, every time a vertex is specified by a call to a GL vertex in the older systems, that vertex immediately goes through the system and is processed, goes off to the GPU and is processed, and that was called immediate mode graphics. The definition of our objects goes through the system immediately, it's displayed as fast as the system can display it, and it's gone. It's not saved at all. It's immediate with no retention. Now, the alternative to that is what's called retain mode graphics, where we take the data, the vertex data, and some other information, colors and other things, and we send that over an array to the GPU, where it might be rendered immediately, it might not be, but it will stay there, and we can store it on the GPU and do multiple renderings, or we can do things like, we don't want to render the same thing over and over again, but typically we'll do things like we'll make a transformation that changes the position or the orientation of the vertices, carry out that operation on a very large amount of data that's on the GPU, not have to send that data over. So there was this tendency, even under the old models, to say they were starting to put things in place that could do a little bit of retain mode graphics. There were things called display lists that let us put information over there. But when we realized the benefits of that, and especially when the modern GPUs not only got much faster, they also started containing a fair amount of storage on their own, then when we got to the latest version of OpenGL, starting with 3.0 and 3.1, we said, it went from 2.5 to 3.0. The reason is that this was a major change, not just a little upgrade. So in 3.0, they said, as of 3.1, we're going to be totally shader based. And all of these, no, there's not going to be any fixed functions around. Those functions were eliminated. The word is, they've been deprecated. It sounds a little better, but it means they were thrown out. And so almost all of the functions that people were familiar with, because most of them did immediate mode graphics, were being thrown out. A lot of the state variables, that we'll talk more about state in the next lecture, that would do things like set the present color or set the current fill pattern, were thrown out too, and there was not necessarily going to be any backward compatibility. They defined two modes, one of which would say, okay, this supports backward compatibility. That was called a compatibility mode. And there was also a core mode which said no backward compatibility. You have to use only the functions that haven't been deprecated, and that means it's a fully retained model, and it has to have shaders. There's no defaults. In the older versions, there were default shaders, so if you didn't want to write shaders, you had a fixed function pipeline. And now we have to, even if the shaders are trivial, starting with 3.1, you have to provide at least those two shaders. So now let's see how WebGL fits into that, and that'll finish this lecture. There were other versions that came along during this time. Let me go down the bottom first. As hardware improved, OpenGL made some major changes, and in fact, if you look at how rapidly it's changing now relative to how slowly it changed starting with version 2, 2.1, 2.2, now it's being changed fairly often. I think we're on 4.3 or 4.4 now, because the GPUs are becoming so much more powerful. Every 6 months there's another level of GPU coming out, that OpenGL is responding to it very, very quickly. So new kinds of shaders have been added. Geometry shaders, we'll talk about a little later, that allow us to add extra vertices. Tessellation shaders that will break up a large polygon into smaller polygons that can be processed simply into usually a lot of triangles, which can be processed very rapidly, and compute shaders that can use the enormous floating point power that's built into the latest GPUs. But the other end of things was the development of OpenGL ES, which stood for embedded systems. So what these were aimed at originally were embedded devices that would go inside some other device, and typically had very low computing power, were very low power devices. They couldn't generate much heat. They really couldn't put great demands on the if they were run by batteries, couldn't with great demands for power. So they wanted a simpler system that would go into this, and that led to first OpenGL 1.0, which was a simplified version of OpenGL 2.1. So it really wasn't a shader-based system, it was a fixed function pipeline. That was then replaced, or another system came along, OpenGL ES version 2.0, which was a simplified version of OpenGL 3.1, and that was the first version that said you have to have shaders. So that's really the core for WebGL, because WebGL is a JavaScript implementation of OpenGL ES 2.0. So it says if it's in, at least in principle, if it's in ES 2.0, it's in WebGL. It's totally shader based. You must write a vertex shader and a fragment shader and provide them. It's written in JavaScript because JavaScript is the language of the web, and the idea was this is going to run in your browser. And in the present situation, as we've said, it'll run in pretty much all the latest browsers now that finally Microsoft has decided not to fight it, and it's supported by the latest version of Internet Explorer. It's been available for a while in the recent versions of Chrome, Mozilla, Safari, Opera, and even on it runs. And because it's sort of very tied in with what goes on embedded devices, which now have been, mostly the interest is in cell phones, is what runs on cell phones. Well, ES will pretty much run on ES2 will pretty much run on Android and iPhones. It's interesting in that I can run my WebGL programs on an Android phone, or at least not all of them, but the one I have, I can run WebGL. Apple supports ES on iPhones, and WebGL is there, but they won't let users access it. So sometime in the near future, we expect that you'll be able to run WebGL on your iPhone too, although you probably don't want to do your development there. You want to do it on probably want to do it on more of a regular computer. So anyhow, this is the present situation, and now we'll move on in the next lecture and talk about the basics of WebGL, what the code looks like, and so on.